talk tonight, we're going to talk about the current situation from a climate perspective and some of the things that we could do, may do, and it's going to be a great chance to look at some of those possibilities going forward. Our speaker, Kelly Wanser, is currently Executive Director of Silver Lining, which is an advocacy group that is working to ensure safety for people and ecosystems by driving options to reduce atmospheric heat. She was previously a co-director of the Marine Cloud Brightening Project at the University of Washington, as which she testified in U.S. Congress for the House Space Science and Technology Committee. And last year, she was also an advisor to the Ocean Conservancy and on the President's Circle of the National Academy of Sciences. Yeah, let's see what we can see from this vantage point about what's in front of us now and in front of us long term as we look at climate. A big round of applause for Kelly.
Thank you for the applause. You can see I have friends in the audience. I'm really touched to be here, and I want to thank Michael and the Interval team and Long Now. They've become something of a home for me, and they're a big part of the work that I've been doing for the past few years, which I will describe. And just to give you a little background on myself, I'm not a scientist. I spent a couple of decades in IT infrastructure, working in the areas of messaging, security, and networks. So I like complex systems problems, and I'm interested in problems with big implications. And about 10 years ago, I became concerned about climate, and as a sort of passion effort, I got to know a couple of people in the area. Steve Schneider, amazing climate scientist who passed away a few years ago, and Ken Caldera, also based at Stanford at Carnegie Institution, who is a mentor of mine in getting to know these topics and understanding them a little bit better. So I've been very fortunate being here in the Bay Area to get an introduction to this type of work and to get to know some of the preeminent people in the field who I'll talk about in the course of this talk. It's a big topic, and so I will be going through some pretty big ideas pretty quickly. So please store up your questions at the end. I've got permission to keep going as long as we need to, as far as questions go. But this is really about looking at the severity of our climate situation. So I'm going to start off by characterizing the sort of challenge that we've got and sort of lining things up in terms of time and space. And then talk a little bit about what people are proposing with regard to near-term options for addressing heat risk. And then finally, I'll talk a little bit about the state of play, where we are and where we might need to go in order to understand and pursue any of these kinds of alternatives. So with that said, I will start with a quote from the eminent thinker, Michael Crichton, which is, "The planet is not in jeopardy, we are in jeopardy." And so in the spirit of Long Now, I kind of want to set the context in terms of the planet that we live on. And the planet that we live on is tremendously complex. I just learned from NPR recently that there are more bacteria on Earth than there are considered to be stars in the universe. So we have this incredibly complex, diverse, abundant system. It makes it incredibly unique in the universe and a little bit difficult to understand and predict, both in the natural system and in the intelligent species that live on it. So we have a complex systems problem, and complex systems problems are characterized by their difficulty in prediction. And they're characterized by the emergence of new things and the death of other things. And so they're quite hard to understand, and they're quite hard to manage. But we have some experience in trying to understand and manage complex systems, which I will talk about. But I want to put this in the context of Earth. And this is the temperature history of the planet, a really nice graph. And you can see that it's not totally linear. So the Holocene optimum, which is the period that we live in, is stretched out a little bit on the chart. But what you'll notice is that we live in this period of incredible sort of temperature stability. And it's allowed the flourishing of a lot of the diversity and abundance that we know. And so what you see in the picture is, a floral composition made by butterflies. And so we live in this sort of delicate space that is a combination of stable temperature. Sorry, I was looking at butterflies and you weren't. So here you go. There are the butterflies. So all of this abundance and delicate diversity is enabled by reasonably stable temperature and rich biodiversity. And you can see from the chart, this is actually quite rare in the history of Earth. And to the best of our knowledge, it's rare in the universe and maybe completely unique. So in this sort of spirit of thinking long term, we have potentially a unique situation in all of history and all of the universe. And it's a delicate one that we're in. And we, as the intelligent species on the planet, have been acting on the system. And one of the things that we've been doing is adding material, pulling material from the ground and adding it into the air in a way that's increasing the amount of heat that the atmosphere stores. And so you can see here in these, we've got a couple of charts that show the increases since industrial times of CO2 and methane released into the atmosphere, and the famous Keeling chart that shows the atmospheric concentrations going up. So from pre-industrial times, we've caused this sort of dramatic uptick in what's coming into the atmosphere that stores heat. And then in more recent times, you can see where that's gone in terms of the past sort of 1,000 years and what's projected going forward into 2100. So you can see in this chart here, sorry, my eyes are failing me a little bit. So we've got the past 100 years, and we're seeing what that's doing to temperatures. And you start to see this rise, especially in the past 30 years, global average temperature. And then this chart on your right is the IPCC projections of what happens to temperature based on current trends. And the red line is called business as usual, and that's actually the line that we're on. And so the other lines, the blue line, which shows kind of a curve and a stabilization, is the most optimistic assumptions about what we might be able to do to keep temperature stable. And I'm going to talk a little bit later about what they're thinking. But in terms of our state as a complex system, one way to think about the Earth system as a biological system like the human body. And there are a lot of similarities to the human body with a fever, where we can handle some amount of spike in fever, but if the fever continues and it continues to rise, then various parts of the system can start to change, and they can start to change permanently. So right now we have a fever, and we want to take a look at what the fever is projected to do to different parts of the Earth system. So these are some of my favorite kids. My godson is the one with the Rubik's Cube, my niece and nephew there. And so around 2050, these kids will be in their 30s, which if you have kids that you know, this will be true of them also. So I want to walk you through some of what's projected for the Earth system around 2050. And this isn't primarily based on climate model predictions like we're used to. This is looking at extrapolations of what's happening to the system now. And this tends to come from scientists and researchers that are looking at different parts of the system individually. And so firstly, we have a projection that the amount of forest burn area in the United States will be 10 times what it was in 1970. So today, it's about 3 times what it was in 1970. And so it's tracking along with temperature rise. So 2 or 3 decades from now, we can anticipate lots more forest fires than we have today. Alongside that, going on at the same time, we'll have the effects of heat on the ocean. And the one that we hear a lot about is the heat effect on coral reefs. Coral reefs support 25% of life in the ocean. And currently, they're being killed by heat stress. They're sensitive to heat. Big heat waves are coming. We've lost somewhere between 1/4 and 1/2 of the coral reefs in the world already. And they support a big portion of ocean life. So we don't know yet quite what happens when we lose that life. And the ocean is a really complex, highly interconnected system. And so heat stress on the ocean could have effects that we can't fully predict in terms of what happens to other life in the ocean and the links between the ocean and the atmosphere. So there's a form of life that grows at the surface of the ocean called phytoplankton. And that biological life is quite important to feeding the fish below. And it also handles interaction between the ocean and the atmosphere. I call it the API layer between the ocean and the atmosphere. So it takes in CO2, it sort of interprets what's happening in the ocean. It's produced by the ocean food web. And then it interacts with the atmosphere. It takes in CO2. It releases gases that help form clouds, and it's very important to our system. Currently, phytoplankton, we're losing at a rate about 1% a decade. And it's thought that in the past since 1950, we may have lost as much as 40% of the phytoplankton on the ocean. So we have to watch for things like this in terms of the whole system. Another thing we have to watch for is collapse of ice sheets in Antarctica. This is a picture by Chris Michael. Chris, where are you? Who has many wonderful Antarctic pictures there, and can talk to you about what it's like to go to Antarctica many times. And so if those ice sheets were to collapse, as they are predicted when temperatures approach around 1.9 degrees, then we might see some big changes, some big abrupt changes in sea level rise and in the nature of the current circulation in the ocean and the major AMOC current. So again, these kinds of things are predicted to happen around 1.9 degrees. And as we saw in our previous chart, we're looking at that around the middle of this century based on what's happening. And again, concurrent with those things, we have effects on infrastructure. So one of the things to think about when we think about climate change, especially when it comes to discussion of adaptation, is we're likely to have lots of things going on at once. And a lot of our infrastructure was built to a certain range of conditions, of temperature, of wind, of storm surge, of ground conditions. And we're starting to push the climate outside of the conditions that some of that infrastructure was built for. So these are two charts. The chart on the left shows the vulnerability of bridges in the United States. And it's forecast that by 2050, about half the bridges in the United States will be vulnerable, meaning they need re-engineered or they shouldn't be used. Half the bridges in the United States. And the other chart is looking at the vulnerability of coastal military infrastructure, which is something that the military takes pretty seriously. And you can see an enormous amount of vulnerability to flooding of that infrastructure, possibly rendering some of those sites unviable. So, and those are just a couple of examples. And I'm not here to necessarily raise alarms, but what I want to do is say, can we think rationally and logically about the set of conditions that we're facing and the kinds of options that we might need to look at? Because heat stress is something that creates a number of big changes and big challenges concurrently that could lead to a lot of suffering for people and a lot of irreversible changes in our natural systems. Good news, we're in Silicon Valley, and I'm lucky because I know the head of research at the SLAC and lots of people in venture capital and people at Stanford at the Precourt Institute and Berkeley where they're working on energy solutions. And the things that are coming in the pipeline in terms of energy, materials, capturing carbon are extraordinary. I'm a techno-optimist, and I believe that by the end of the century, it's absolutely possible that we could have solutions to waste, to energy, to food production that allow the sustainable, healthy, happy life for people on this planet for years to come, and big natural systems that sustain themselves too. So